Hey everyone, welcome back to the Basic Aeronautical Knowledge series. Today we're talking about the International Standard Atmosphere and why it matters in aviation. The International Standard Atmosphere, or ISA, is a model used in aviation to define standard conditions of temperature, pressure, and air density at different altitudes. In this video, we'll break down the International Standard Atmosphere and how it applies to your flying. The International Standard Atmosphere, or ISA, is a model used in aviation to define standard atmospheric conditions at different altitudes. It provides a consistent reference for temperature, pressure, and air density, allowing pilots and engineers to make accurate performance calculations. By using ISA, we can compare real-world conditions to a known standard. This helps in flight planning, aircraft performance calculations, and altimeter settings. While ISA represents an ideal set of atmospheric conditions, actual weather may vary significantly. Understanding how these differences impact flight is essential for every pilot. In the next section, we'll take a closer look at the specific values of ISA at sea level and how they change with altitude. The air around us is made up of a mixture of gases, and understanding this composition is essential for aviation. The Earth's atmosphere consists of approximately 78% nitrogen, 21% oxygen, and 1% other gases like argon and carbon dioxide. These gases are what create the air density that affects flight. Now, how does this relate to aircraft performance? Air has mass, weight, and density, which play a key role in generating lift. Mass, air has substance, meaning it can exert force on an aircraft. Weight, air is affected by gravity, just like any other object. Density, the amount of air in a given volume affects how much lift an aircraft can generate. This ties directly into the International Standard Atmosphere, ISA. ISA provides a reference for how air density changes at different altitudes. As we climb higher, the air becomes less dense, reducing lift and engine performance. Pilots use ISA to adjust for these changes and ensure accurate flight planning. In the next section, we'll explore the key temperature and pressure variables and their influence on atmospheric conditions and aircraft performance. Air density plays a crucial role in aviation, as it directly affects lift, engine performance, and overall aircraft efficiency. But what factors determine air density? Air density is influenced by 4 key elements: temperature, pressure, altitude, and humidity. Temperature. Warmer air is less dense because the molecules spread out. This means lower lift and reduced engine performance. Pressure. Higher pressure compresses air molecules, increasing density and improving aircraft performance. Altitude. As altitude increases, air pressure decreases, leading to lower air density and reduced lift. Humidity. Moist air is less dense than dry air because water vapor is lighter than oxygen and nitrogen molecules. More humidity means reduced aircraft performance. On the left, we see warm air molecules. They are spread out, making the air less dense. On the right, cold air molecules are packed closely together, creating denser air. This ties directly into the International Standard Atmosphere, ISA. ISA assumes standard conditions of air temperature and pressure at different altitudes. Pilots compare actual conditions to ISA to adjust performance calculations. For example, on a hot day, the aircraft may require a longer takeoff roll due to lower air density. As air density decreases, it directly affects the performance of an aircraft in 3 key areas: the engine, the propeller, and the wings. Engine performance. With lower air density, there is less oxygen available to mix with fuel, reducing engine power output. Right? This means the aircraft may struggle to generate full power, right, especially at high altitudes or in hot weather. Propeller efficiency. A propeller generates thrust, right, by pushing air backward. When air is less dense, right, there are fewer air molecules to push against, reducing thrust and overall efficiency. Wing lift. Lift is created when air flows over the wings. In less dense air, there are fewer air molecules available to generate the necessary pressure difference. As a result, the aircraft may require a higher takeoff speed and experience reduced climb performance. This is why pilots must consider air density when planning flights. High altitude, hot temperatures, and humid conditions can all reduce air density, requiring longer takeoff distances, reduced climb rates, and adjustments to fuel and power settings. The International Standard Atmosphere, ISA, helps pilots calculate these performance changes by providing a standard reference for air density at different altitudes. In the next section, we'll look at lapse rates and how temperature and pressure change with altitude. The International Standard Atmosphere, or ISA, provides a standard reference for atmospheric conditions at different altitudes. At sea level, ISA defines specific values for temperature and pressure, which serve as the baseline for aircraft performance calculations. Temperature at sea level, right, the standard temperature is 15 degrees Celsius. As altitude increases, temperature decreases at a lapse rate of approximately 2 degrees Celsius per 1,000 feet. Pressure at sea level, right, the standard atmospheric pressure, right, is 1,013.25 hectopascals, or 29.92 inches of mercury. As altitude increases, pressure decreases at a rate of 1 hectopascal per 30 feet. Why is this important for pilots? ISA provides a predictable way to estimate how temperature and pressure change with altitude. Real-world conditions may vary, but by comparing them to ISA, pilots can make necessary adjustments for aircraft performance, fuel calculations, and altimeter settings. In the next section, we'll look at how deviations from ISA affect flight performance. Right, the International Standard Atmosphere, or ISA, right, is a crucial reference in aviation. Right, but why is it so important? Aircraft performance calculations. ISA provides a baseline for performance data, helping pilots determine takeoff distances, climb rates, and fuel burn under standard conditions. Right. If real-world conditions differ from ISA, pilots must adjust their calculations accordingly. Comparing actual conditions to standard conditions. Since real atmospheric conditions vary, ISA allows pilots and engineers to compare the actual temperature, pressure, and density at any altitude to a known standard. Right, this helps in assessing how different conditions will affect the aircraft's performance. Altimeter settings and flight planning. ISA is also essential for setting altimeters correctly. Since pressure changes with altitude, aircraft use the standard sea level pressure of 1,013.25 hectopascals when flying at high altitudes. Right, this ensures that all aircraft are using a common reference, improving airspace safety. By understanding ISA, pilots can anticipate how their aircraft will perform in different weather conditions and make the necessary adjustments for a safe and efficient flight. Right, you will learn more about this through your flight training and studies. Thanks for watching this episode of the BAK series. If you're just starting your aviation journey, make sure you subscribe so you don't miss out on more essential lessons to help you ace your flight training, and check out teamaviation.com.au for more resources. Hit that like button if you found this useful, and leave a comment below with what you want to learn next. See you in the next video.